So, this lecture will focus on system modeling approaches. In previous lecture, we provided background of system modeling approaches and all that. Now, this time this lecture has been designed in such a way that you yourself can analyze a system and how which are the different aspects of system modeling that need to be addressed. We'll try to explain this particular part. So, let us see what is a system. Okay? When we talk about risk monitoring or reliability monitoring, so this is a system, let us say a energy system here we are trying to represent. So, as I have been insisting, the system essentially comprises of process system for normal operation of the plant. So, like normal core cooling, shutdown cooling, normal shutdown system and reactor regulation system. Okay. So, these are the system when the system is in operation and when it is to be normal shutdown, then these systems are active. But then other part and of course, before we talk about this system, let us talk, this is central to our modeling. Reactor system, source of energy, let us say. So, these are the required, and there are many systems. There are tens of systems. I have shown you only important system just to give you an idea what we mean by systems approach, you know. So, this is the reactor system, and as long as this is safe, everything is good about it. Okay. Whether it is a cooling requirement or shutdown requirement, timely shutdown requirements are met, regulation, the reactors have to be regulated. So, they are put it in the category of process system. Okay. Now, the other side is safety system or mitigation. So, emergency shutdown system. When we are not able to shut down through the normal system, then emergency shutdown system comes into the picture, and then safety system, mitigation, emergency. So, this is secondary category. We call safety system, let us call them safety system. Then second one is emergency shutdown system number 2. So, what we are saying, if the normal shutdown system fails, then there are two, you can imagine the kind of redundancy that are built into the system, so that the safety of this particular structure we call reactor system is ensured actually, you know. And then similar thing with the power supply. If emergency power supply system, it could be AC or it could be DC. I am sorry, here it should be DC. So, DC AC power supply should be there, okay, for emergency power requirement of the plant. And then emergency cooling system. If normal cooling system fails, then there should be a emergency cooling system. First is shutdown cooling system and then emergency cooling system. These two things should be there actually. Okay, now this is a reactor, and reactor is providing the deliverables. So, we require health maintenance of process system. If there is anything wrong, this emergency or safety shutdown system, they come into the picture. Though plant will be shut down, but then the core or the plant will remain safe in terms of consequences. Okay, and then this plant, at least for the nuclear plant, we can say these systems, they are generally in a containment. So, that means anything goes wrong, the consequences will not be in public domain. Okay, and they are deliverable, means in nuclear plant the objective is nuclear power plant, the delivery of the power and to the grid. Okay, and then there is an interface control room. The control room of the plant oversees health of all these systems. Okay, so and these are mimic panels. I have not shown various indication charts, all those things, and you know. So here the operator keeps observing and ensures that plant operation is safe. At first level, there are automatic provisions. Okay, so they ensure that plant is safe. but in case the any action is required or corrective action is required, the human and team they are there to take care of it. So, in short, I wanted to give an overview of what a system means. There is a control room, there is a human maintaining, and there are areas of the plant where these systems are located. They are also made. Delivery is some throughput is there. Here it is a power, and then control room is fed with all the information, production logic, control logic, all this information come to control room and ensure that plant is safe. Okay. So, this is our view of system over here. So, again I will repeat, process system and safety system, these are the two broad categories. They make up the plant, and then there is a central agency which is called reactor system. Ensuring health of this system is very important. Okay. Health of this system and the component connected to this system like pipes, and other detectors, sources. So, they should be safe and they should be functioning to ensure the safety of the system. So, now if we see major safety and reliability modeling approaches. What are the approaches? Previous slide we talked about it, but then I want to bring to your attention that how systems are modeled. So, you can see there is a traditional deterministic approach, probabilistic approach. These things are very new actually, but the deterministic approach it has done well for so many years. Why it has done well? I am saying because this approach has ensured and brought, if I talk about the nuclear industry, is one of the safest system if you compare with the any other systems, So, that is why this approach, and essentially deterministic approach was the thing. But then as the time passes, we have experience, we have data, we have computers, and then you require all these tools to further fine tune system performance and understanding of the plant. So, we have this as far as the reliability engineering is concerned, we have this models. This is reliability block diagram, then fault tree analysis, event tree analysis, Markov model, and fuzzy approach. Fuzzy approach probably you might not have heard, I am not sure about it, but this approach is required to model mostly imprecise parameters. Let us say expert opinion, as I discussed in the previous lecture. Expert opinion is there, it comes in the linguistic variables. It's a categorization, or its a quality will be like very good, good, not good. So, how to convert them? Because for risk modeling in quantitative we require a quantitative model. So, fuzzy approach, it enables conversion of linguistic model to possibility of this approach. And probably there is an assumption, if our possibilistic approach and probabilistic approach they are near, or there is an assumption, we can consider this approach acceptable to probabilistic modeling also. Now, structural reliability. So, this what we talked about is the system reliability, but normally the structural systems like pipes, and they can also be called as a passive systems. This modeling has to be done by stress strength model, and so this is another. So, there is one more reliability matrix that is called not time varying, where reliability is not a function of time, but reliability is a function of cycles. Like if I have a relay, how many times it has gone on off in a year, that will determine the life. Okay. So, number of cycles also could be one of the metrics for reliability, and it is used in PRA model. It is nothing new as such actually. Then structural reliability, yes, if I have to understand the margin, stress strength margin, in traditional deterministic approach they used to call safety margin. Okay. But now we have a probabilistic method. Why probabilistic method? Because now data is available. So, we can see the failure probability overlapping area between stress and strength, and that is how we can directly give a failure probability of a structural system. That could be a pipe, it could be a vessel, it could be some wall, some whatever. So, but generally we talk about structural system, a passive system and all. Then probabilistic assessment is performed at level 1, level 2, level 3. Level 1 is a system approach, level 2 is a release category from the plant, and level 3 is consequences in public domain. And one more method other than the PRA, we have this failure mode effect analysis. I would call this is a family of FMEA. So there is one more entity in the family. Yes, this is a failure mode mechanism effect and criticality analysis, and then failure mode effect and critical. They are used as and when system specific requirements are there. But at the higher end, this is a FMEA approach, and they are other family members. And supporting tools for these things are establishing deterministic design criteria when we talk about this, human reliability and common cause failure, thermal hydrolysis and lifestyle. So when we go for modeling of this, these are the tools and methods that are required for electronics. It should be MIL Handbook 217 plus or FIDUS. This is relatively new handbook methods that has been developed, and MIL 217 and 217 plus has become as like mainstay. But here the analysts now argue that this should be replaced with the physics of failure approach. Of course, it is resource intensive POF, but then in certain location it is required to get more confidence. PRA software, there are commercial softwares that are available, and then open literature. Lot of open literature support is required, whether it is you can call regulatory guide or codes or standard. And here Bureau of Indian Standard, it is developing a standard on PRA. It's about to be released in a couple of months. So this is the status. Representation of integrated and holistic PRA methodology. Now here in this slide, we will discuss how other individual tools and how PRA captures their essence actually, or the tool itself, you know. So let us say, and this PRA model, now slowly we are drifting to, or we are giving the confidence that probabilistic risk assessment is the ideal best approach for risk modeling, because it delivers essence of all the other tools and methods that are available. So how we realize this? So here we are telling representation of integrated and holistic PRA methodology. So it involves, there is a tool called plant hazard analysis. Normally it is used in chemical industry, but in PRA it is used as a support for identifying the initiating event and at qualitative level, you know. And then we have this probabilistic evaluation of system structures and components. There we have a conservative principle, redundancy, diversity, they come from deterministic study. So that means the essence of deterministic study is also coming over here, and international codes and standard. Okay, they are deterministic as well as probabilistic also. So both comes here and gives us a confidence that this method has got a very rational base, quantitative method. Then thermal hydrolytic and design analysis. Though PRA in PRA thermal hydrolytic and design analysis don't form it, but when we have to assess the uncertainty associated with the result or its performance, then it is used here, and it is basically from deterministic part of the analysis which goes. If I talk about the failure criteria, then for thermal hydrolytic system, then it goes as an input to the PSA model along with the uncertainty. So it is integrated into the PRA model of the plant. Structural and design analysis, and then process control and this and the quality attribute, plant configuration and probability system success criteria. So these three tools, they allow us to model the system success criteria, or conversely speaking failure criteria, plant configuration and all. So that means when we develop a PRA model of the plant configuration in the form of a fault tree, event tree, it becomes part of it. Not only that, it provides a quantitative estimates of their failure. So that gives more confidence, and basically what we discussing now is a part of risk based or risk engineering approach, risk based or risk informed approach, because deterministic input is there, probabilistic input is there, and then we are creating other tools and method like FMEA family comes here, and fault tree analysis, because a component failure, which mode, what are the mechanism. So only at least those components which are important for the fault tree, for them failure mode and effect analysis is performed, and then event tree analysis. So these two together will give a fault tree analysis. Okay. And so this has given a, these two together will, and along with the FMEA will give a qualitative model of the plant. We discussed earlier. First stage is qualitative model of the plant. Then plant, from here we come to plant hardware, software and human reliability data. This is giving us PRA with failure data assignment. So now we had a qualitative model, we have failure data assignment, and then finally we have a Monte Carlo simulation along with here. So that will give us uncertainty, and finally CDF. But before that, the plant hardware software, this module, this requires statistical probability, theory of evaluation and all, and then Markov model is there, and fuzzy analysis is there. This together and the input coming from here, it gives a failure assignment, and that is how core damage frequency or damage frequency and uncertainty statements are carried out. So you can see many methods are there in PRA. This slide captures, and that is how we do. We feel PRA provides a robust rational based and quantitative framework for modeling of risk actually or safety. Now PRA for system modeling, if I again put one more yardstick and try to see its capability evaluation. So first we have seen in the previous slide, it captures all the approaches or almost most of the approaches, and other approaches which we will not discuss, it will be used as and when it is required, like structural analysis for crack propagation. And if you have to give a crack failure crack probability, I have to use complete domain of probabilistic fracture mechanic. So that comes here. So but we will discuss as and when certain things, issues come or subject comes. Then evaluation of PR capability. PRA capability provides a very quantitative estimate. So it is discrete in the sense along with the uncertainty and all, and then power of integration. I mean this particular matrix, it gives us a rational based approach for arriving at the correct decision, because in the PRA model a component connection to the top, what is that connection in terms of uncertainty, in terms of failure probability, and what happens if that component fails. So everything is, so a huge advantage of power of integration is offered by PRA framework. Graphical framework, it is for our eyes to see and understand and track the things or diagnose issues, so that are available here. Okay. And then holistic, it is holistic in the sense that it combines deterministic also, if I talk about it as a risk based or risk informed approach. So if I say PRA being used as a part of risk informed or risk based approach, it becomes holistic in nature. Then quantification of component we have discussed, uncertainty also Monte Carlo simulation that is characterizing the uncertainty, and here we are talking about aleatory uncertainty. And if there is epistemic component, it also tells that you have to work on it, whether it is a data or whether it is a design issue. Only we can live with the aleatory uncertainty which we have to manage. Okay. A powerful tool for decision making, where safety, conservatively speaking, rising the overriding factor. So when I say at one point that safety or risk is a overriding factor, then I should have an equally strong method that is holistic, integrable, rational based and everything. So we have this thing over here. Other reliability tools, FMEA family, fault tree, event tree, Markov model, logic diagram, naturally a part of PRA. They are part of PRA. So we say it is a holistic approach, where different things being earlier they were dealt in different way, maybe for a specific application, but PRA provides a holistic framework when we want to see integrated results. Now modeling a process system. Modeling a process system, let us say first step we said identifying the initiating event. So loss of offsite power, loss of coolant accident. This is we are in the context of a nuclear that we are talking about, loss of regulation accident and loss of flow accident. And there are many. This it contains, the initiating event list contains tens of events that form the list of the initiating event. Okay, and then there are more than tens of that means and then the frequency having like for LOCA is it is considered normal if it is 1 into 10 to the minus 4. So now that much of learning or feel factor is there that from the quantification we can have again back to qualitative thinking and representation actually. So just for the example, I have dealt in detail how initiating events are derived, actually frequencies are derived. See, let's say there is a plant, there are 10 events have happened, not 10 events, these are years, year 1, year 2, instead of telling year number, I am telling 1, 2, 3, first year, second year, third year, 10 years data we had, and this is number of power failure frequency, total number of power failures are 13. So loop failure frequency is 13 divided by 10. Isn't it simple? We got such a powerful statement that from my plant average failure rate frequency is 1.3, and then I go one step further for drawing the event tree. Okay. So and then before we go to the next step, we have example of failure mode effect analysis. Let us see, I will explain you. There is a component code, reactor protection system, power supply, CAP. There is a one aluminum electrolytic capacitor C is there. It is 100 microfarad. Now I am doing FMEA. How it fails? Capacitor solder joints and cooling arrangement. That we are boundary we are making, because in FMEA we have to create the boundary of the system. What is the limit we are considering that component comprised of? Quality attribute mill screen. If the component is American military standard follows, so this kind of informations are required everywhere when we talk about the component quality. Failure mode and fail to supply, power supply failure, okay, local. So this is how failure mode effect analysis is done, and then frequency is occurrence is moderate. The moderate definition, it will be rating will be given in a separate matrix, detection rating, and then this is high, that means it gets detected. Precursor to this is increase in harmonics and across. So this is the, you can say, precursor here. Okay. So if a capacitor degradation somebody wants to understand, this is the matrix that is available. Severity is very low because it doesn't might not be impacting because of redundancy and diversity. Okay. And then consequence corrective actions, either repair, replace, and all those things will be there. So this is the failure mode effect analysis, and along with that we should have the information about operating environment. Suppose if the component has a information that this capacitor should not be operated more than 48 degrees centigrade. So what I require is my environment in the place where the capacitor module has been kept, or the electronics, power electronics has been kept, mode of operation online standby with this also should. So this support the FMEA, complete FMEA, and it gives a sort of a judgment what kind of system we are dealing in. So support information is very much part of the FMEA. Now in previous slide we were talking about the event tree, and we got the frequency. So not event analysis that we talked about it, and then now we have a system analysis. There is an emergency system, power supply system in a plant. So when the grid failure occurs, this system comprising of 2 diesel generator set, it takes over and it ensures safety of the plant through 2 buses, emergency bus A and B, and there is a inter tie breaker, because suppose if this diesel generator does not come, then this can be supplied through a tie, and when the power supply failure has occurred, these 2 breakers should open. Okay. So this is now, and then long term safety can be assured, and these are the loads on bus A, these are loads on bus B, and then physical separation. This is a classical example of common cause failure. So if any fire is there on this diesel generator, it should not affect this diesel generator. So there is a wall between these two, and that's how common cause failure is finds a central place even during the design, operation and maintenance also of the plant. Okay. And then we created a fault tree. So fault tree, the result can fail either independently. So bus A and bus B will be affected. So unless until these two diesel generator fail, this failure will not occur, independent failure. And why bus A will fail? Because of diesel generator or breaker 1, or diesel generator 1, and bus B diesel. So you can see how we are going from top event to this is a OR gate. If we go to this event either through this route or through this route, this is a common cause failure. Common cause could be bus A and B. If there is a fault at bus A and B, flooding in the area, let's say some short circuit occurs due to flooding, and both the diesel generator fails, fire in the area, both the diesel. So you can see how common cause failure accounts for the redundancy being killed over here. Seismic event, they can bring in the common cause factor. We'll see in details what we mean by common cause failure, but you would have understood. And now if I take the independent failure, if this diesel generator failure is 10 to the minus 3, this is 10 to the minus 3, so we get 10 to the minus 6 on top. But if a common cause failure, which is normally taken as 0.1, so if you see 10 to the minus 3 individual failure probability, and common cause if we take 10 to the minus 4, the emergency power supply system failure probability comes to 10 to the minus 4, which appears realistic also. But if we take only this branch, normally our books and all they quote when they model it, if you don't take common cause failure, you will be giving a very optimistic estimate of the system failure. Let us say I have given here 10 to the minus 3 here. Okay. Now, once now we have developed the emergency power supply system. Okay. Similarly, other systems also will be required. So we have come to event tree. So initiating event, let us say loss of offset power, how much frequency we got? 1.3. We will plug in over here, and then we will create then plant shutdown. Yes, shutdown is required. We saw in first slide, plant shutdown system should activate, emergency power supply should activate, and reactor control, reactor cooling should be ensured. So if we take care of these three functions, we are safe. In the event tree, this is a loop tree: up success, down failure. If plant doesn't get shut down, then itself then it doesn't matter what. So unsafe state become. But if a plant shutdown happens, but emergency power supply system is not there, then there will be consequences, because reactor coolant system, reactor cooling system will not be operating. So now again, if emergency power is there, then also so this we have already done that it is safe state. If it is not there, we are going to the unsafe stage, because reactor cooling is very important for the system. So these are the three damage category, and this three frequency, if I the way I have done for loop, if I do analyze the fault tree and have the quantification, I can have quantification of these two, and adding these three accident sequence frequency, these are called accident sequences. I will get the damage frequency for the plant. So what an elegant framework. In a simplest, the event trees are, I have given you a very simplistic perspective of a plant, but it is sufficient for you to understand what plant means actually. So in this we saw fault tree, event tree, systems approach, and then preliminary fault tree we have drawn, generic PRA model we have given, and probably now in the second lecture you should know what PRA means, which we are advocating as one of the best approach for risk assessment, and a simplified procedure has been demonstrated.